Okay guys, in our previous videos we have already learned on several rule of derivative. We also learned on how to conduct differentiation in a situation where you have functions inside another function, in a situation where you have mix up of variables x and y. And there is one more situation that might happen, right, which is a situation that allow you to use parametric differentiation. Okay, so parametric derivative is a technique for finding derivative when x and y depend on another variable, which is t, usually thought of as time. Now this x and y function, right, usually represent the point. We represent the function to locate where is the point in your graph. Right? You have point x and point y, right? For example, if you look at this, they give you two functions for x and y. If you plug in any value of t, you will be able to locate the coordinate in one Cartesian coordinate graph. Okay, so usually one way to differentiate these things is actually to plot the graph that made of this x and y and find the derivative as usual. But there is another way where we can find the derivative without doing that, which is by conducting parametric differentiation. So for parametric differentiation here, this is the formula that we are going to use. So dy over dx equal to dy over dt over dx over dt, provided that dx over dt not equal to 0, because if dx over dt equal to 0, of course there is no operation that can be conducted here. We cannot divide with 0. Okay, so look at this formula. Do you realize something? Do you feel any familiarity with this formula? Okay, remember that previously we have learned on one formula that is, if we change a bit, we will have the same formula. It is known as chain rule. If we try to move the denominator here up, you will get dy over dt times with dt over dx. That is chain rule. But then for you to apply this formula, I mean the formula of chain rule to solve of this problem, we might encounter with some situation, right? Because if you look at this, x will be given in a function in terms of t. The same goes to y, will be given in the terms of t. So if you differentiate these two, you will get dx over dt, and the same goes for this one, dy over dt. If we want to apply chain rule, we will need to first change the function. We'll need to move we'll need to make a function, right? We need to change it back so that the function will become t in terms of x, right? It is sometimes not possible for certain functions, so that is why we do it like this. Okay, so let's try to differentiate using parametric differentiation on exercise 4.1. Solve for dy over dx for this question. We have x with this function and y with this function. So let's try to find the derivative, right, by using these two information. This will be the formula that we're going to use. So basically this is the formula. We'll need to know dy over dt and dx over dt. So we have x in terms of t and y in terms of t, so we can just directly look for this information. Dy over dt is equal to negative 2 sine 2t. You can refer to the trigonometric derivative again later. dx over dt is 1 minus 12t squared. Right? Now we have these two information, we can just plug it in into our formula. So dy negative 2 sine 2t at the numerator and 1 over 12t squared at the denominator. So if it can be simplified, please do. If not, this will be the differentiation of these parametric equations. Alright, so by doing this, right, when you have any t that you want to look at, right, when plug in the t in these two function, you will able to locate the coordinate. Right, at the same time, when you have this function, right, additionally you can also determine the slope. Remember, dy dx is to find the slope. So by inputting the value of t here, you will be able to also find the slope. Okay, let's try to do the next one. Okay, we have these two functions of x and y. Right, again we'll need to find for dx dt and dy dt. So this is it. Dx dt is equal to 2 and dy dt is equal to 2t minus 5. The next thing to do is just to plug it in and you'll have your derivative. Okay, so that is for parametric differentiation, which is quite direct. Now let's look for the next one, tangent and normal line. Okay, this is the line that I mentioned earlier, right? Tangent line is a line that is touching the graph at the point where you want to look the curve, where you want to look at the slope. Okay, so tangent line and normal line here is just a straight line. So the formula that they are going to use will be a formula of a straight line, which is y equals to mx plus c. Okay, so the equation of tangent line, okay, at any point x1 and y1 is this, right? Y equal to mx minus x1 is to represent the x plus y1 represent the c, y-intercept, right? And the equation of normal line will be this. If this later will be the line that is perpendicular to tangent line, which means that it will have a position of 90 degree from the tangent line. Okay, so let's look at it. Let's try to just do the exercise. Before we proceed, let's look at the graph here. Okay, if you have this is x squared, which is the graph of x squared, again quadratic. If this is the tangent line at x equal to 1, as you can see, when you draw the line, it actually touching the curve at 1, x1, right? That is a tangent line. And of course you will have an equation for that. And then you can also look for the normal line, which is a line that is crossing exactly 90 degree from the tangent line at the same point x1, right? So let's do the exercise. So you don't have the exercise, let's try to do the example here. Let's try to look at the second question. Fx equal to x squared minus 2x plus 1. That is the function. Alright, that is the function. Right, it is still a quadratic function. You can imagine that the curve is just like a U curve. And they want us to find a tangent line at point x3. So what will be the equation, the straight line equation, which is known as a tangent line at point 3 that is touching this curve? Okay, so let's do that. Let's look at the needed information one by one. So we know that the straight line is equal to mx plus c. Specifically for the tangent line, this will be the equation y equal to m. X is actually x minus x1 plus y1 to represent the y-intercept. So let us look for m first. What is m here? M is the slope. And remember, to find the slope in difference is actually by looking at a differentiation of this function. Okay, so we differentiate the function, we get to x minus 2, and the slope at point 3, right? X3. So we just substitute 3 in x and we'll get 4. 4 will become the value of m, or the slope. So basically the slope will be a positive slope. We can imagine it is this way. Now let's look back at the equation. We now have m, but we still need to find other things, which is x1 and y1. Of course, x1 is actually being given, which is 3 here. So we need to figure out what is the value of y when x is 3 on that graph. So let's figure that out by substituting our x into the function. So in a situation where x3, fx or y will be equal to 4. So x1 and y1 is 3, 4. Now that we have everything, the next thing to do to have a complete tangent line function is to just substitute everything. So y equal to m, which is 4, times with x minus x1, which is 3, plus with y1, which is 4. Simplify it and you have this as your answer. So basically this is your tangent line. Now the next thing to do is to find the normal line. Remember, the normal line is a line that is completely perpendicular to the tangent line, right? We're going to find that using this formula, similar with a different slope, of course. Okay, so let's try to do that. We already have all of the information, which is m, x1 and y1. Then the things to do after that is just to input everything. So we have 4, 3 and 4. So just calculate it and you should get negative x plus 19 over 4 as your straight line that represent a normal line at point x3. So that is how to calculate normal line and tangent line, right? Thank you.